Welcome back. In this video, you will learn to design a feedback controller and simulate the closed-loop system using PID. In particular, we will add a PID controller to the double integrated system that we created in the previous video. All of the example code for this video can be found on my GitHub page linked in the video description below. Let's get into it. To implement our controller in Drake, we need to add a new system to our diagram. To implement any arbitrary controller, you can design your own LeafSystem, but there are lots of built-in controllers in Drake that you could use as well, including a PID controller. Then we will just connect the input and output ports of the controller and the plant, and then add loggers as needed to plot the results. I recommend adding a logger to the output of the controller and the plant so you can verify that the controller is working as intended. First, you need to choose your controller. Make sure you know the size of your input vector and your output signal. In our case, the input size is 2 and the output size is 1. At this point, you should also note what parameters you will need to implement your controller. For the sake of simplicity, we will use a PD controller which drives the state of the plant to some desired position and velocity, x1d, x2d. I will show you how to implement this as a LeafSystem, but if you stick around to the end of the video, I'll also show you how to use Drake's built-in PID controller to save yourself some code. In Python, we define our controller by inheriting from LeafSystem. In our init function, we first declare the input and output port sizes. When we declare our vector output port, we also pass in a callback function which we call self.output. The name of the callback function can be whatever you want. I just went with self.output. Next, I like to set the parameters of my controller, which are my controller gains and target state. Finally, we implement the controller in the callback function. Note that we can read the input port during this callback function using the context object. Once we are happy with our controller, we can add it to the diagram. We connect the output of the plant to the input of the controller, and the output of the controller to the input of the plant. We also add a logger to the output of both the plant and the controller. Just like we did in the last video, we set the initial conditions and simulate our system. Notice that our controller does not contain any states, so the total number of continuous state variables in our diagram is still just 2. We can access the loggers to make plots of the simulation. I've put together a few tasks for you to complete in order to get practice with implementing your own feedback controller. There's some starter code that provides you about 90% of the code needed for your simulation. You'll need to fill in all the to-dos in the starter code. You can also modify your plant dynamics like we did in the previous video and see how this affects your simulation. Solutions to these tasks can be found on my GitHub page. Here's a video of me running the solution on my machine. First, we see the diagram that we created. We have the double integrator, our controller, our vector log sync here, and our vector log sync there. Next, we'll see our position versus time. Also have the velocity versus time graph. And then finally, we'll have the input versus time plot. Okay, now let's go through the extensions. First, we'll replace our LeafSystem PD controller with Drake's built-in PID controller. So if we go to the documentation real quick, we see that the PID controller has 2 input ports and 1 output port. So the first input port is this estimated state. This is what we're going to be feeding the output of our plant into. The desired state is just going to be held at some constant reference. And then, of course, the control signal goes to our plant input. You can see over here, this is the control signal that's being calculated. We're not going to use this integral term, so we'll just set ki to 0. Now, if we scroll down, we'll see how to create the PID controller. We see that it takes in a constant vector kp, ki, and kd. So we'll set this to 0, we'll set this guy to 10, we'll set this guy to 5. If we keep scrolling down, we'll see how to get the input ports and the output ports. So here's the estimated state port, here's the desired state port, and here's the output control port. So we're going to have to connect all of these with builder.connect. Okay, now let's go to the code. So at the very top, we have all of our input statements. Then we have our double integrator implementation. This is the same as the first video. You'll notice there is no implementation for our PD controller anymore. So now let's create our diagram. So we'll create our plant as before. For a controller, we're going to use the PID controller constructor and make sure that you pass a list for the KP, the KI, and the KD. Next, we'll add a reference signal. This will just be a constant vector source, 1, 0. Next, we'll connect the output port of the controller, followed by the 2 input ports of the controller. Then we'll add a logger to the output of our plant and the output of our controller. Then we can go ahead and set our initial conditions. So because we added this PID controller into our diagram, the context has actually changed a little bit. This is because the PID controller contains a single continuous state, and that's for the integral term. So what we have to do is to actually get our subcontext from our diagram. So what I mean by that is that the plant, our double integrator, is going to have context with 2 continuous states, and our controller is also going to have context with 1 continuous state. So together we have a total of 3 continuous states, and I just like to set them separately. Then we'll create the simulator and run the simulation, and then we can go ahead and plot these. So I'm just going to run this again. Okay, here's our diagram. We see we have our double integrator connected to a PID controller. We see the estimated state and the desired state input ports. Desired state's connected to this constant vector source, and then we're logging the output of the double integrator and the output of our controller. Then these plots should look identical to last time because we have the same plant, same initial conditions. We just are using Drake's version of the PID controller instead. For extension 2, you can add a saturation block between the controller and the plant to define a minimum and maximum input into the plant. This is pretty realistic to add to your simulations, and you should give it a try. For extension 3, you should replace the double integrator plant with something more complicated, such as a pendulum. Try to add a PID controller to move the pendulum to some angle. As a further challenge, can you make the pendulum balance vertically? In the next video, I'll introduce you to the simulator config class, which allows you to change the default simulation options to give you more control over how your Drake simulations are run. You'll also see how to make your loggers record data at a fixed rate, which is something that you can't do easily in MATLAB. If you found this video helpful, please be sure to leave a like, subscribe so you don't miss the next video in the series, and leave a comment if you have any questions or if you have another video request. See ya!